Okay, so this is our last problem solving session. Uh, so since we are over six, we can start the session. If they want to join, they can uh, do in the middle. Like yeah. So otherwise, like if someone wants to have this session, like they can also access it through the recording session, which would be available on YouTube or also somewhere. You can get it from your portal as well. So let me share the presentation right now. Okay, so yeah, this is the last problem solving session. Uh, so over the last few weeks, we have discussed on various topics, and the one which we really looked on is to solve differential equations. That is one prominently we have gone through in various uh, other discussions so far. So, hi Nachiketa. So, like I was just starting right now, so I haven't like gone into the topic yet. So, okay, so just starting now. So this evening, like we would be discussing on range functions and series solution methods. So first of all, like, are you able to hear me now, Nachiketa? Like, would you get my audio? Oh, okay. Thanks. So thank you for your confirmation. So okay. So let's begin our last problem solving session. So we'll be looking on routine function and a series solution method. So these are the two things that were discussed in this week's of your NPTEL course. So this is again a brief review of what green functions are. So green functions again, like you can check uh, on your portal. Those lectures are really nice. You can get a very fruitful intuition of how and what green functions are actually and how they are useful to you. So just for a quick review, like I have given like what usually happens in green functions or what you normally do with green functions. So suppose like if you have a like differential operator like this. So this is some differential operator. So like these are your derivative operators. This is your second derivative, and this is your nth derivative operator. And corresponding to each of these, like you have a like a coefficient term. So that is some that can be some function of your dependent variable. Uh, I'm sorry, that can be some function of your independent variable. So in this case, here it is t. So that is what a differential operator normally would look like. And when you add the differential operator on, on your dependent variable, like here in this case it is f, so you get something g of t. So this is for the case of inhomogeneous. If we would be looking for something of homogeneous type equation, homogeneous type differential equation, it would be something uh, y of t equals to 0. So this is for your homogeneous type equation. So so when you have such inhomogeneous equations, inhomogeneous differential equation, what happens, like if you want to solve those inhomogeneous equations, there is another elegant way to extract its solution, and that is using green functions. So these green functions, this g of t prime. So what happens, like when you operate the same differential operator on this function, that is g, you get delta functions. So exploiting this property, like we get what uh, the solutions for your inhomogeneous differential equations. So we'll see how that happens. Like how we do that, actually we begin with this kind of answers. Like here f of t is integral of dt prime g of t prime, this small g t prime. So what happens if you think this is your um, uh, answers, or the solution of a differential equation. So like we have some differential equation, let's say something del square del t square plus something uh, c1 del t something c2 f is equals to z, and its solution, this f, can be written as this, where this g is your gain function. So uh, like to see how this is all happening, like we can do a quick check here. Like let's say if I'm uh, putting this solution in my differential equation, this one, so you will see that like this entire thing is my um, differential operator. So I can uh, quickly tell you that when L of t is operated on this answers, so that is, here you can see I can take this, I can add this differential operator inside this integral, because this integral is only with respect to your variable t prime, but t is some other variable that in which I mean that is actually our independent variable for our case. So I can take that inside it, because here you see that L of t contains derivative with respect to t only with t. So it's not derivatives with respect to t. So I can take that in. So that will be L of t, g of t prime, and it can only act on uh, only on G, because G has T in it, function of T prime. So that's why this L of T, this differential operator, can only act on this G T T prime, because it contains T, and the other G, that is the small G, uh, that do not have any dependency on T. Instead, it has dependency on T prime. So so that differential operator that won't act on the small G. So here, so again, what I was telling, exploiting this feature of this green function right here, like I can write dt prime L of g dt prime is your direct delta. That is the property of green function, and that is multiplied with small gt prime. And when you solve this, again, this is from your Dirac delta property. Like when you solve this integral, it is simply g of t. So you can you can check back your last like your lectures on Dirac deltas, where when you had this kind of integral, when you have some function multiplied with delta function and it is integrated with uh, in this way, then your uh, integral values basically just you capture the uh, mm, you capture your uh, like non-integrated variable instead of your dummy variable, and inside your inside this function. So these are called test functions, and that is what the result of your integral. So if you like could not able to remember this, like I would like suggest you to go back there and you can see how this integral comes. So it's just simple like just a direct use of property that I have done. That's it. So that is how like you can see here. So I finally obtained L of t f of t is g of t. So you can see that this differential equation is what this answers is satisfied. So this is the answers which I have taken, and I substituted in f of t in the differential equation, and in RHS I got g of t. So that is what you can able to do with this green function, because I used a property right here when this differential operator acts on this green function gives delta functions. So uh, one such case, like we can move on here uh, by understanding this kind of differential equation which I've given here. So let's say like you have a differential equation which is y double prime plus omega square y is equals to g of t, and its initial conditions. These are basically your initial conditions. If I write a little better, so so at 0 your y and its derivative both are 0. So when you have this, this is your given differential equation and this your initial conditions, then how you can use green functions here in this setup? First, you write your differential equation. So okay, um, yeah. So and another way to say is like one way is to say is like you pick a answers like this with the help of green function in it, that is g of t prime inside this integral, and you put it in your differential equation and you will find what is the form of z. Now once you find the form of z, then you get your solution. And the other way is around, like or like it is the other way of saying the same thing is like when you take your g, that is here I am writing g to be something of this. So this is the g I am writing here in terms of integral of delta function, because that is again using the property of delta function. And uh, and then you see here, and I'm also substituting the answers of y, because for this differential equation y is the solution and y I am substituting to be this. So uh, so in doing this, you will find that like you will compare both the sides of this equation. You will find this is your main equation. So this is your main equation to determine what is g, what is your green function. So because once you get the green function from this by solving this differential equation, the only one thing to do is like you have to put this z, this green function which you will obtain from here inside your answers. So this is your, so okay, let me write somewhere down here, or like simply I'm like this is your answers. Okay. So once you get the form of z by solving this differential equation, which is I have boxed it here, so you can simply put it in your answers, and once you put in your answers, you get your uh, solution for your ordinary differential equation. So how can you solve this differential equation to get z? So that is basically first you do what you can do. You have to take a Laplace transform of this. So these things are again well explained in your lectures, which has been uploaded in your last week. So you can check back if there is any other like verification or some more like understanding you need in detail, then that is your best place to do. But just for the sake of flow, like I put it all these things once again, just to make you remember what was going here. So yeah, I was telling you. So if you from here you have to uh, like you from here you have to find what is g. So to do that you have to take Laplace transform. So the Laplace transform of this differential equation is basically this thing right here. So again, like I have given some this Laplace transforms uh, 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 this properties right here. Using this properties you can get the Laplace transform of this differential equation. So um, so this Laplace transforms again, like we saw in the last week, like how we can solve ordinary differential equations using Laplace transform. It is the same thing we are also doing here. There is nothing bigger difference lies here between what we are doing today and also last time around. So yeah, so you do the Laplace transform, and once you do the Laplace transform, you will get some kind of uh, uh, you will get some kind of this algebraic type equation, this equation right here. So so this is like what we are doing, like we are in this Laplace transform, like we are going from uh, t variable to p variable. So like some Laplace of some, let's say some f of t that we are performing here, then that actually gives us some, let's say z of t. That is what we are doing here. So yeah. So this s square g of s, which is appearing right here. So for this case, like the Laplace transform was taken from t variable to s variable domain. But here, like just to avoid some confusion, like I am using this t variable. So you can use any variable you like. So there is no any like fixed rule to that. So yeah. So once you get this algebraic type equation, and the next thing is to solve this yeah, what happens, like after when you reach this point, so you take you estimate what is the value of this L of g t t prime, that is the Laplace transform of your gain function. So you get something like this. And once you get, so what you have to do, because your final aim was to determine what is your green function. So but here you have calculated what is the Laplace transform of your green function, but you have to calculate g, that is your actual green function. So this is something, let's say g of some this is something g of s t prime or p t prime. So that is your Laplace transform of green function. But when you but from this step, you have to calculate what is g of t t prime. That is only the part which is inside this Laplace transform braces. So this g of t t prime, you can obtain it by taking the inverse Laplace transform. So that is what, if you remember, that is what basically exactly the same thing we were doing last time around as well. So so that so now your g of t prime will basically, so you have to take the Laplace transform of this thing, inverse Laplace. So do inverse Laplace on both the sides. So here you have g g t t prime, and here also uh, so sorry. So let me make it clear right here. So this is So do Laplace inverse on this side, and also uh, do Laplace inverse on this side as well. So once you do that, or obviously if I was right initially, uh, okay. So you just do Laplace inverse on both the sides, and you will get what is G. So Laplace inverse in your LHS, Laplace inverse of Laplace of G of t, that is basically G of t, equals to Laplace inverse on your right hand side. So that will give you this thing. So again, to get this Laplace inverse, you can use the properties that we discussed last time around. The same property will put it here. You'll get this. So, and once you get G, and then you are done there because you only need G to get your solution for the differential equation, because you initially chose your answers to be something y of t equals to 0 to t. Uh, so you have g of t prime and g of uh, what was that? So yeah, uh, so this is your answers. Okay, mm, I think I have written this fi. This would be g. G. Okay, yeah. So you got what is g here. So you substitute the form of g right here, expression of g inside this, and you get a solution. So that is what I have written here also. This is the answers that you take. So that is what basically you have to do to solve your different ordinary differential equations uh, using green functions. So you first you pick a answers in the form like of this form, and so in the answers you have g, your green function. So the next thing is to determine what this green function is. So to determine that, you use this differential equation which I have shown right here. So when you use the differential equation, then you have to solve this differential equation for z, and that you can do that by taking Laplace transform. You will get a difference. You get an algebraic equation, and then you solve that algebraic equation to get what is g, and that you can get it from by taking again inverse Laplace of that equation. So that is what we were doing here in this step. So yeah, that is how you will obtain your final solution. So again, so uh, so suppose if you have like in this first uh, question right here, so you have uh, this is same what we have discussed right now. So here in this case, you see in the first bit, the first part of your question, this f of t is something sine omega t. So and rest everything same, your initial conditions and uh, yeah, and also remember we have also used our initial conditions before. So I can tell you where exactly. So here in this step, when we were actually uh, doing this Laplace transform, here we have used the initial conditions right here, this one at this point, and this, and also this one right here. So here you use initial conditions, and you will see that this two will be zero, because your initial conditions are y of zero and y prime of zero is zero. So that means your y of zero is zero, and you are taking your answers also something of this form, y of t prime g of t prime and g of t prime. So if your y at 0 is 0, that means your z is basically 0. G of t is 0. Y of 0 is 0. That means g of 0 t prime. This is 0 t prime is also 0. So that is the condition which I was using in this. So after yeah, so we can see like one of these questions right here. So the here also what I was telling you, everything remains same, but your f of t, I have picked up a very specific uh, type function of f of t, that is sine omega t. So just you have to uh, this is not f of t, that is basically g of t, I think. Yeah. So this g of t, this g of t, we have sine omega t. So, and let's say initially I kept it some generic type function g of t. Now I am taking this very specific form of that function, that is sine omega t. So in that case, just use the final form, because that is the only thing that is changing right here to get your solution. So your solution would be y of t to integrate that 0 to t uh, over omega sine omega t minus t prime, and that is multiplied with your g of t. So that is actually multiplied with the g of t, because this is your uh, RHS part. In the RHS part is g of t, but when you take this g of t inside your answer, this will be g of t prime. So you will write your g of t is sine omega t, and g of t prime will be sine omega t prime, and you integrate this the whole thing with dt. Sorry, dt prime, so that you will get your solution in terms of t. So once you do this integral, like you will see that uh, uh, basically you will use your uh, trigonometry rules right here. So uh, this is of the something of form. Yeah, you can use like sine A sine B type formula over here. So once you do that, like you will get 1 by 2 omega cos of omega t minus 2t prime, and then um, minus cos of omega t, you integrate with this pt prime, and when you do that, you will get um, so like and this the integral is straightforward. You can check it. So this will give you sine omega t by 2 omega square minus t by 2 omega cos omega 2, and this will be omega. Okay. Yeah. So that is your solution for your given differential equation. So that is how usually you can use your twin functions to get your solutions for your inhomogeneous type differential equations. Then the next question was the case where you have f of t of this form, 1 when it is between 0 and a, uh, otherwise it is 0. So here you will see that uh, this function, like last time or around also, I told you like I can write this function in terms of unit step function. Like you can remember like unit step function or something defined like this. 1, 0 if t is greater than a, otherwise. Also, this a has to be greater than 0. So, uh, this is your definition for unit step function. And so, the same when you have a is 0, that is t minus 0, that is basically u of t. So, that will be also 1 and 0 when your t is greater than 0, or else it will be 0 every time. So, you can write this f of t in terms of u of t. Uh, um, t minus u of t minus a. So that is how. If you think some like, for example, uh, you have some, uh, let's say your t is greater than a, then in that case, uh, your t is greater than a. So in that case, for t greater than a, you will have 1 minus 1, that is 0. Because according to this unit step function, you will see whenever your t is greater than it will always be 1. So in both the cases, it will be 1. So so when you're uh, for the case when t is only greater than 0 but less than a, so t greater than 0, that will be u of t will be 1, but u of t minus a will be, so this is for the case t greater than 0 and t less than a, u of t will be 0. So in this case, your f of t is basically 1. And for the case when t is greater than 0 and also uh, not this, yeah, these are the two basically the conditions. Yeah, so this is for t greater than a and also t greater than 0. And is there any more conditions? uh, yeah, there will be another one condition if t is less than 0 and also t is less than a. So in that case also your f of t is basically 0 minus 0 0. So uh, that is what the idea of this unit step function. And why I was doing writing in terms of unit step function, because you will remember last time around, like I have showed you, like using this unit step function, there is also a very specific form of Laplace transform. You can use that property or feature directly in this problem to get your answer quite easily. So the same thing like you will do here because you know what is your f of t. So your f of t is basically this right here. So this is your f of t. So you got a f of t. Now you want to calculate your solution. So your solution is y of t dt prime. You are integrating with some derivative variable t prime g of t. This was your answers uh, that you chose earlier. So your sorry. So so this is your answers you chose earlier. But from like just now we found out what is g of dt prime, this green function. Whenever you have a differential equation of this kind of form, so your green function will always be uh, so in this case we have this g of t. So this is every time it like poses a lot of confusion, so sorry for that. So yeah. So now you use your green function right here. So your green function is basically 1 over omega sine omega t minus t prime, and your g of t prime is basically what I told you just right now. That is u of t minus u of t minus a, u of t minus u of. So this will be u of t prime because here you are using g of t prime, u of t prime minus a, and you integrate it with dt prime. So then you will see that you have to split this integral because uh, so let me write g of t sine omega t minus t prime of t, then 0 to t sine omega t minus t prime t prime minus a dt prime. Okay, so then basically what you have to do, you have to uh, like pick a case where t is less than a, and then you have to pick what t greater than a. So for t less than a, so for t less than a, so let me show you. So okay, let's take first what is t greater than a. So for t greater than a, you will find that uh, first actually you have to again you have to split this integral like of this form. You can check for t greater than a, you will see that uh, 0 to t, this will be 0 t minus t prime u of t, then so integrate it with dt, so dt prime. Then minus a to t uh, sine omega t minus t prime. So there will be no u of t dt prime, and this is dt prime. So I'm using this for t greater than a. I'm using the idea of the step function which I have given here, and accordingly you split the integral, and you will see that for t greater than a, the your integral will only survive from between a to t for the second term, because you see that when your t is greater than a, only then this step function is non-zero. So this is non-zero for t greater than a. So so that is why I'm doing this right here. So and yeah, and then when you do this, like you can find out like when you evaluate this integral, you will get 1 over omega. So like I'm writing this integral, so this integral again, it is per step proper. You just do the integral, and you just have to put the limiting values. So this will give you uh, the entire expression will be something like this: cos omega t. So your cos omega t minus a minus cos omega t. So, okay. So that is for t greater than a. So for the same way, like you can also do for t less than a, and for t less than a, you will see that uh, your integral will basically reduce to this 0 to t sine omega t minus t prime dt prime minus 0, because your second part will never contribute, because second part you have t prime minus a. So for u of t prime minus a will be 0 when you are taking when you are taking t less than a case. So when you are taking t less than a, so that step function or that heaviside function is basically 0. So that's why we won't get any contribution from the second term, but the first term will have. So the first term, the only long term that will survive, and when you integrate this, you will again get something of this form cos omega t by omega. So you just have to integrate and use the limits, and then here you get 1 over omega square 1 minus cos omega t. So yeah, so basically that will be your final solution. So you have the solution in two parts: 1 over omega square 1 minus cos omega t, and 1 over omega square cos omega t minus a cos omega t. So this is for t less than a, and this is for t greater than a. So yeah, so this is what your final form of your solution would be. So so did you able to get this? So Nachiketa, if you there's some problem in following anywhere in this, was that fine for you? No. Okay, let me know if you uh, could not follow somewhere. Okay, okay, briefly. Okay, sure. So, so what I was doing here, so basically, I here you see uh, um, the differential equation which is given here. That is something v double sorry y double prime plus omega square of t, and you're using green functions to solve this kind of inhomogeneous equation. So to solve this inhomogeneous differential equation, that is to get what is y of t. So you pick a answers. So that answers is this one, which with the help of green function. So this is your answers that you use select, and so in that answers your z is unknown to you, that is your green function. So you have to basically determine what is your green function, but we have already told you before that your g will be always of something of this form, which is given right here. This is your g when you have when you have differential equation of this form with these initial conditions, that will be your g. Now, once you have the G, you can easily calculate what is your solution for differential equation. That is, you can get what is your y of t. But to do that, you see that now you have to you also have a very specific form of G. That is, sorry, again, uh, this will be Z. So this G of t is basically uh, is 1 and 0 when it is 1, when it is when your t is between 0 and a, so otherwise it is 0. So you have to put this g of t prime in this integral, and then you have to solve, and after solving this integral you will basically get what is your y, that is your solution for the differential equation. So the same we are also doing here. So this is for your first part. In your first part, that is quite straightforward. So your g of t was sine omega t. I just simply put it here. I substituted this sine omega t prime and just calculated this integral. The second part, your g again. This is g. So g of t was 1 and 0. 1 for this is between 0 t and a. So again, I'm sorry. I have messed up here and there with the notation of G and F. Okay, so this is G of T. So now I have this form. This is the form of my G finally. And again, to get my solution, that is Y of T, I have to simply use this G of T prime form inside the answers or inside the integral that I'm using. So again, this is our main answers. So again, you have to use the form of g of t prime inside this. So this is the g of t I am having right here, and I will use that inside this, inside that answers. And when you substitute this g of t, that is what I am doing right here. So here I have substituted. This is your g of t prime. This is your solution. The entire integral, this entire thing is your solution. So, and then from here basically you have to solve this integral, and there is a bit subtlety right here. You have to carefully see, like because you are integrating with some limits. So you will see that when your t is basically greater than a, you will see that your uh, your RHS, your like I mean in the second, the first term, here you see this u of t is 0 whenever you have anything greater than so this u of t is basically 1 whenever you have anything greater than t greater than 0. So that this is non-zero for t greater than 0. So since I'm taking p is greater than a, so this will be equal to 1. And here in the second part, you will see that since I'm taking t greater than a, u of t prime minus a will be also 0. But you will see that we are integrating from 0 to t. So from 0 to a, and then from a to t, there is a so let me, okay, I would have been a bit more specific in this part. So this integral, you can split this integral from 0 to a dt prime, then plus a to t dt prime. So this integral again will be 0, because you will see that for t less than a, because I'm picking t greater than a. So for t greater than a, this the second part will be non-zero. That is what unit step function is basically telling me. Uh, so here, so only for t greater than a, the c of t minus a will be 0. Otherwise, it will be 0 otherwise. So only for uh, t greater than a, this will be 1. So that's why uh, I have this final form, and you integrate it, you will get this solution. Then you pick another limit for t less than a. So for t less than a, again, your first the first term will survive, because t less than a, that is something which is or let me say a is greater than 0. So that is basically this case, or not this. So a is greater than 0, and yeah, uh, this is this case. So in this case also, like you will see that like your second term will completely go away. Only the first term will there, and that is again you do this integral and you will get. So so is this clear? Like or again somewhere you could not follow. So finally your answer will be in two parts for t less than a and t greater than a. So this is for t less than a, and for t greater than a this is. So so did you follow this, or again some more clarification required, you can tell me. Okay, okay, fine. So thanks. So then we can move on for the next part. So now like I have a different uh, form of differential equation of this time. So initially it was like something y double prime plus omega square y g of t, but now it is this here. You see that in the second term I have a negative sign right here, and the initial condition stays same. So you will see that in that case, the green function, you will follow the same process, just the process that we did earlier, just right before our previous discussion, where we determined what the green function was. That came out to be something of sine omega t minus t prime by omega. So here you have sine hyperbolic instead of sine omega, and here you have 1 by a instead of 1 by omega. So everything remains same. Only the in this green function, this sine hyperbolic will appear instead of sine omega, and I can also tell you like how that is happening in which exactly at what point we will find the difference. That difference you will basically find. Uh, um, yeah, right here. So in this part, you will see like when we were taking this inverse Laplace right here, we basically got 1 by omega sine omega t minus t prime. So in this case, when you take in this case also you will obey the same process step by step in the exact manner. But in this part, at this point, when you will appear that when you will take Laplace inverse, uh, you will find that instead of sine omega t minus t prime, you will get sine hyperbolic omega t minus t prime. So that is the change you will see. Otherwise, everything will remain same. So 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 that will be the final form of green function, and then you will have again just when you after the moment you are getting your green function, you just put it in your answers. So and when you put it in your answers, your y of t will give you the solution of your differential equation. So again, like we can check quick examples right here. So uh, so second, is there any different question in my just a minute. Okay, so okay. So here also, like first part, same process you have to do. uh, Like uh, so your f of t is one when you have 0 to a, that is your t. So your um, and your f of t is 0 when your t is greater than a. So again, you will use that same approach. Suppose trying to say right here, there is another form which you can use. So, for a different question, right? Okay, so this is like similar question which I did right here. Can do this the same thing which I did. Like you split the integral and you have to calculate it. So basically, maybe I can quickly tell you what is the idea right here. I was looking for some different question, but I was not getting at the moment. But otherwise, this is also fine. So what you have to do, like again, you put this thing in your answers. That is uh, y of t 0 to t some hyperbolic a t t prime of t prime dt. So again, here also you will do this same splitting. Uh, First, you will calculate for t less than a, or like same way like which we did, t greater than a. You will get a. You will have to solve this integral. This is a to t t prime, and when you solve this integral, you will find yeah, find a form of I of t, and after that, then you have to do for t less than a. For t less than a, there also you will do the integral y of t. So that integral, like I can just simply tell you the non-zero parts. So this will be dt prime minus 0 to dt prime. So the same thing here also you will repeat. Just like here, the only difference is like earlier you had sine omega t and now you have sine hyperbole. That is the only difference right here. Otherwise, when you do this, like you will find like everything remains in the integral value will be different just because sine hyperbolic is appearing right here. Uh, and then the next step is basically, uh, I think after when you have the solution for t less than a, let me check. Is there any more difference? Yeah, I mean that is just that there is no other difference. Like the integration, like you have to see a bit carefully. Otherwise, uh, the idea is basically the same. So I'm writing down the same form. So you can check it like if there is any problem, you can uh, let me know. I can do it for you properly. And so now we can look for some other questions right here. So I'm writing down the final answer right here. This is T, this is T greater than A, this is T less than A. So okay. So that will be your final form of the answer. So everything remains same. Only sine hyperbolic is appearing right here instead of sine omega. Rest all process you can follow the same. And then the next question, maybe this one we can see a bit more properly. So the second part, you have f of t is t. So in this case, like let's say uh, your uh, you put this form, this f of t in your answers. Again, the same uh, strategy: sine hyperbolic a t minus t prime, then e minus t prime, and you have to integrate this with dt prime. And then again you have to solve this integral and and also the previous one thing you can do, this is a very uh, handy and I mean this is a handy trick to solve this integral. So uh, use this substitution that will give you say cos hyperbolic a t minus t prime. So, you take sine hyperbolic a t minus t prime to be something new, and so it's uh, d would be something of this, and this is uh, dt prime. I'm taking with this to dt. So yeah, then here you will see that your du is basically uh, okay. And one more substitution like you can do here is you take dv equals to e to the power minus t prime and dt prime, and v equals to it minus e t prime. So using the substitutions, like you will find you can write this u. Uh, wait a minute. Okay. So when you do the substitution, the okay. So the first when you try to solve this integral, you have to use this by parts. So for that, like I have taken, so for by parts, I have taken the u to be my uh, sine hyperbolic and v to be my minus e to the power minus t, and then uh, dv and du would go like this, and then you will see that your in your by parts, the first part will give you uv because in byparts, what you do, the first term is UdV. So UdV, basically when you integrate dV, that will give you V. So this is V t to U limits. There is a negative sign, so the limits will be reversed. Then the second term will be 0 to t V du. So yeah, so you basically have to just use the byparts, or simply if it is confusing, you apply byparts directly, write it, and then you use the substitutions, and then you will see that uh, in the first part, like you will get your solution to be something. Uh, this is e minus t prime. So sine hyperbolic a t minus t prime. Uh, then substitute p and 0, say 0 to t cos hyperbolic a t minus t prime t prime dt prime. So yeah, so when you do this integral further, you will find uh, uh, here you will see that like you will get something of this form. Mm, if I call this integral as something I, and this I will be minus 0. So here on the only thing is the integral is bit trickier. Otherwise, it is the straightforward problem. Once you know the what is your form of g of t, or what you know green function, you put that in your answers, and also you put the RHS part of your answers, and then you solve the integration, and that is your solution for the inhomogeneous differential equation. That is only the thing that I am doing here, and the rest part is the integral. That is something quite time taking. Otherwise, it is very straightforward. So I can write this as this is minus 0. Yeah, same times. So this will come from this part. This is a minus t and 1. So here again you have to do another by part. That is that will give you this, and this thing minus a times I. I is basically again you get the same integral. So this is I 1 minus a square equals to sine hyperbolic at plus a bt minus a cos hyperbolic at. So this I will give you sine hyperbolic at plus a et minus a cos hyperbolic at, or 1 minus a. So yeah, so that is your y of t. So y of t is basically 1 by a I, and so here you got it. What is your y of t? So that is a cos hyperbolic at minus a et sine hyperbolic at over a 1 minus a square. So this is what the result you will get, the solution for your differential equation. So the only trick part here is only the uh, integral which you have to solve. Otherwise, like it is simply straightforward. You put your green function and your f of t in your answers right here, and you get your solution. So is this key? The previous one was playful. Uh, just a differential equation. Like just you have to check yourself. Like you get okay. So then this is a different topic where you can solve your differential equations using some series solutions. Like what happens like in general, the differential equations that you solve, you basically like pick a answers, and that answers is in naturally is a is in the form of some series expansion. Like for example, when you were solving this differential equation, you used to get some solution something of the form uh, exponential x and exponential negative x. So these were like this exponential x were like 1 plus x plus x squared by 2 factorial plus x cubed by 3 factorial and so on. So these were the expressions for uh, uh, your solution. So like so this answers that you were initially taking, like you may remember for this uh, differential equation, the actual solution or something coming out to be of this form. So you will see that this exponential of x and exponential of minus negative x, I can write something in this series expansion or the basically the Taylor expansion. So or like overall, like you see that like we always uh, um, get a solution, something of the series solution. So that is inherently it is already uh, existing. That when you solve differential equation, you get some form of polynomials, some higher order polynomials, and so on. So it is the same way. Like here also, we were getting something of sine x and cos x, and this sine x basically you can write uh, 1 or the sine x, its expansion would be something x minus x cubed 3 factorial and x fifth factorial and so on. So this is again another series. So these were uh, your some uh, way that you were estimating or you were basically determining the solution for your differential equations, where you were basically picking some uh, specific answers, and that answers within the answers inherently there exists a series, series form of that solution. They basically converge into a particular form of function. So, but and why you were able to write those answers, why you were able to write those things, because they satisfy this differential equation. Uh, uh, Given that your differential equation, you see, uh, did not contain any terms like, let's say, d square y dx square plus p of x y equals to 0. So this p of x was some constant for you last time. So uh, for we used to always say that you used to solve ordinary differential equations with constant coefficients. But what happens when you have this kind of p of x which is not constant? So in those cases, you only have one choice, that is you start from a basic idea of series solution. So that is what will be the discussion following from here. So what you do, like first uh, like the what are basically analytic functions? Like analytic functions, like let's say a function f of x, when you do the Taylor series expansion of this f of x, Taylor expansion uh, about some point x naught, you say that like that expansion or that series basically converges to f of x for all x in the interval of convergence. So like the one which we were telling, that when you were doing Taylor expansion of sin x, you get some series, and this you were expanding about zero. Taylor expansion about zero. So this is again like when you do Taylor series expansion for a given function, and when you see that entire sum of that series actually is giving that function for every value of x, then that function will be your analytic function. And at certain point, like there exists like for certain value of let's say like in the sine x, let's say there exists some value for sine x equals to x naught. You will see that yeah, that for x equal to x naught, the series that I have written here, you will find that that will diverge basically. That will go to infinity, or basically uh, it will give you some other high value, something of divergent nature. You will find that sine of x naught that never gives any divergent value. So because like sine values like goes from uh, -1 to 1. So, uh, but here in this series, if you are getting for particular value of x to be divergent, then that won't be a uh, analytic function. And sin x is an analytic function because it do not have any diverging nature in its series expansion, or basically in its Taylor series expansion. So that is what series, that is what analytic functions are. So we'll basically see the functions that we will be looking, the coefficient of these differential equations, which I was telling you, which are not constant. Like we will see whether they are analytic or not. If they're analytic, like we will see if they are not analytic, there is a different way of treating them, or there is a different way of determining their solution. So, like for example, when you have different ordinary, like when you have a differential equation like this, um, so your P and Q are some polynomials of nx. So again, that is not constant. So let's say if there exists a point x equals to a, which is your ordinary point if P and Q do not diverge for x equals to a. So let me tell you what is basically this ordinary point from this example. Let's say I can write this differential equation d square y dx squared by x by 1 plus x squared and dy by dx minus y by 1 plus x squared equals to 0. So this is basically my p of x, and this is q of x. So this is q of xy, is p of x dy by dx. So okay, so your q of x is 1 by 1 plus x square, and p of x is x by 1 plus x square. You will see that your p of x by 1 plus x square, and q of x is minus 1 by 1 plus x square. You will see that at x equals to 0, you see at x equals to 0, this is something 0, and this is also at x equals to 0, this is minus 1. So at x equals to 0, we can say that this is a point where your p of x and q of x are behaving analytically. Like that is why we can say that this is an ordinary point. X equals to 0 is an ordinary point. Is an ordinary point for this differential equation. So x equals to 0 is an ordinary point. Is an ordinary point. And here you will see that when you rewrite this differential equation, you will get p by d square by dx squared plus 2x squared minus x by x squared dy by dx plus 1 by x squared and y equals to 0. Here in this case, here p of x is 2x squared minus x by x squared, and q of x is 1 by x squared. And in you will see that in both p and x at x equals to 0, p goes to something infinity, and also q or 0 also goes to infinity. So that's why x equals to 0 is not an ordinary point in this case for this differential equation. So So that is the idea of ordinary point. And uh, like you can see example like how we solve differential equations involving this p and x type polynomials, which are not constant coefficients. So you basically assume a series like this. Like again, these things uh, would be well explained to you in your lectures. You can check them if you want to know in detail, like what is happening in this part of discussion of only differential equations when your coefficients are not constant. They are instead some polynomials. The idea to solve uh, the idea is to solve those differential equations when p and q are some analytic functions. That is, like there exists some ordinary point for P and Q. The process is to follow these steps. First, you assume answers again of this form. That is, uh, y is some form of series expansion. Like this is, I can write for k going to 0 to like infinity a k x to the power k. So then you take its derivative and then double derivative. You substitute them in your differential equation. So substitute your dy by dx, d square by dx square, and y. This is your y. You substitute them in your uh, differential equation, and you will find that where you will compare LHS and RHS of a differential equation. You will get you will can by comparing the coefficients you can calculate what is a2, a3, and so on in terms of a naught, and further you will get a recurrence relation where you will get a relation something ak something expression for ak. So you will determine what is ak from here, and once you get this ak, for you will check for different values of k, and for when you calculate for different values of k, you will basically get all your this unknown coefficients right here, which we should put in your answers a0, a1, and a2, ak. And then once you know your unknown coefficients, and that will give you. So these are the coefficients of answers. So once you get your exact form of coefficients, then you get your total solution. So that is what you do. So in this kind of uh, techniques or methodologies where you pick a answers, and in that answers there will be something unknown. You determine that unknown by using some process, and once you get that, you will have your final answer. So like one example we can quickly check here. So like so in this question as well, um, 1 minus x square d square y dx square minus x dy square plus 4y. So again, here you will see that we can your p of x is minus x by 1 minus x square, and q of x is 4 by 1 minus x square. In both this case, you will see that at x equals to 0, uh, at x equals to 0, both are analytic, so it is an ordinary point. U of x and qx are defined, so it is an ordinary. About like for when you try to solve this differential equation for the case when you have a ordinary point, so you adapt this process. You follow these steps. So start from the answers. So you take answer something of this form ak xk, and then you would take its derivative, that is basically a0 plus a1x plus a2x square and so on plus and x, and this goes. Then you take its derivative y prime. You will see that like uh, a1 plus way to x plus 3 at 3 x cube, so on. This will be n a n x n minus 1. So this will be, I can write this summation a k k x k minus 1. Same way I can you take another derivative, and that you can write summation a k times k minus 1 x k minus 2. And then the next step is to, so uh, your next step is, that is your third step. So you will substitute them in your differential equation. So space. So when you substitute them in your differential equation, so that is 1 minus x squared d square y by dx square. So in d square y by dx square, I will substitute my double derivative. This is your d square y by dx square. So you will substitute this a k minus 1 k minus 2 minus x summation a k k x k minus 1 plus 4 summation a k x k equals to 0. Okay. So then, um, yeah, then the next step is to like use solve this, you simplify this expression. So like when you simplify this, you will get something k minus 1 x k minus 2 minus summation a k minus 1 x k plus a k k x k plus, so when x square is multiplying with the first term, so that is x to the power k. So from here I'm getting these coefficients, and yeah, for the last is this term. So yeah, so I've just multiplied this 1 minus x square factor, so with the first term, and then I have rearranged with the rearranged it with xk minus 2 and xk terms right here. So you here you see that like I can basically like you have effectively you have two terms, that is k minus 2 ak xk k squared minus 4 equals to 0. So then like yeah, that is what we put here. Now the next thing is to calculate uh, yeah, next thing is to you have to calculate this coefficients a2 a3, and these things like you can see that if I can get in RHS like I have 0, that means the coefficient of x to the power k is 0 on RHS. So like in RHS I can write something 0 times xk minus 2 plus something 0 times xk. So coefficient on RHS is 0 for xk term. So that, one more thing, like what I can do, I can substitute k with some k plus 2, k to k. So I substituting k to k plus 2 here, uh, because when I substitute this k to k plus 2, here I can basically making xk minus 2 to xk, and this remains the same for second part. So effectively, like I will have ak plus 2, k plus 2, k plus 1 minus ak, k square minus 4 equals to 0. Because in RHS, I have uh, the this is your basically what happens. This term is xk equals to 0. That means this entire thing is 0, because here xk cannot be 0. That means this factor has to be 0. So when you solve for this factor, you will get ak plus 2 equals to k square minus 4 by k plus 2, k plus 1 equals to ak, that is k minus 2 by k plus 1 ak. So this relation is basically your recurrence relation. So when you have the recurrence relation, then you just simply have to determine different values of uh, different a values, that is a0, a1, a2, and so on. So and that is what you can say, like for let's say for k equals to 0, you have a2 equals to minus 2 a0, and simply so for k equals to 1, you have a3 equals to minus a1. So so when you keep doing this, you'll find so this will be 0 by 3 a2 equals to 0. So when you do this, like you can get all your forms of your uh, like basically your a values. So for k3, like I'm directly writing if I will be minus a1 over 8, and 6 is 2 by 5 equals to 2 by 5, 0, that is 0. So now you substitute all these values of a in your answers that you assumed initially. So that is a0 plus a1x to a0 x squared plus minus half a1 x cubed plus 0 x4 plus minus a1 by 8 x5 plus 0.x6. So that is 0 multiplied x6 and so on. So this will be your final solution of y, and you see that like still there is two coefficients which is unknown, that is a0, a1, and you are getting final answer in terms of all in terms of a0 and a1. Why this a0, a1 is still unknown? Because you are solving a second order differential equation and you need two initial conditions, that is what not provided in this question. So you have to only end your solution with those two coefficients being unknown, because that can only be determined if there is if initial conditions are given, like y of certain x equals to a, some would be some b or something, and similarly y prime, you need to know some initial conditions, and if that initial conditions is given, then you can estimate what is a0 and a1 as well. So from here basically you would have got a0 and a1. So so that is like uh, you can solve a solution about when you are solving a ordinary differential equation about an ordinary point. Now what happens, like if that is not the case, if you want to solve about an singular point, like for example, like oh, no, before that, like what is basically singular point? So singular point is something which you would have already known, or you could have already guessed from the discussion just we did right just moments back, where you had p and q functions, and if that function diverging instead of some other finite or zero value at some point x equals to a, then that point x equals to a is called singular type point, is a singular point. Then further, that is not the clear specification, because you further have two kind of singular point, that is regular and irregular. So regular is something if they obey this condition x minus a times p, x minus a whole square times q do not diverge at x equals to a. The first thing you have to check, like at x equals to a, whether p and q are diverging or not. If they are diverging, then that is your singular point. If they are not, then that is your uh, normal ordinary point. So if they are diverging at x equals to a, further like x equals to a, that means that is your singular point. X equals to a is your singular point, and further you have to verify like what kind of singular point it is, whether it is regular singular point or irregular singular point. So to do that, like you check x minus a multiply x minus a to your polynomial function p of x, and x minus a square to your polynomial function q of x, and then again you check at x equals to a whether they are diverging or not. If they are not diverging, then that means that x equals to a is your regular singular point, and if it is diverging, then that x equals to a is your irregular singular point. So basically, a regular singular point diverges diverges at x equals to a for your p of x function and q of x function, but not for x minus a p and x minus a whole square q. But for irregular singular point, it diverges on both the cases. Like when you apply, when you put x equals to a in your p of x and q of x, and also as well in your x minus a p and x minus a square q. So that is what your regular and singular points. So this is a quick example to see like calculate what find regular singular points. So this differential equation I can write 3 by 2x dy dx plus x square minus 4 by 2x square y equals to 0. So here p of x is 3 by 2x and q of x is x square minus 4 by 2x square. So here you see that x equals to 0. So p and q are not analytic. So x equals to 0 is a singular point. Then further you have to check whether what kind of singular point it is. So uh, let me clear out some space. Okay. So here you have to check what kind of singular point it is. So first you multiply x with p, that is 2x, that is 3 by 2, and then you see that at x multiplied p at x equals to 0, this is equals to 3 by 2. So this is not diverging. So that means you can right from here you can guess that this is your uh, regular singular point. So so you have ensured that x equals to 0, which you claim to be singular point, that is exactly regular singular point, because at x times multiplied p at x equals to 0, it's not giving 3 by 2. Also you have to check x square q. This also you have to check, because either one of them goes to zero, then you will see that like that won't be your regular singular point. It can be your irregular singular point. So again, like you can check at x square cube at x equals to zero. This would give you uh, uh, yeah. So this is giving -2. So so that means they are not diverging, not diverging. So so this is so x equals to zero is a regular singular point. The same you can check for a regular singular point for this case. Uh, Here also, like I can directly write what is p of x. P of x is basically 2x minus 2 by x, x minus 2 squared, or that is basically 2 by x, x minus 2, and q of x is x plus 3 by x multiplied by x minus 2 squared. So again, to check, so x equals to 2 is your is a singular type point, singular type point. Now, what type it is, you have to further verify from xp. So at xp at x equals to 0, you will see that, sorry, we are checking it. So like there are two singular type points here, one x equals to 2 and also x equals to 0 is also a singular type point, because you will see that in denominator there are two values of x by which it can the denominator can be 0. One is at x equals to 0 and the other is at x equals to 2. So at x equals to 0, first you check what kind of singularity it is. So at x equals to 0, you will see that this is something like 2 minus x minus 2 at x equals to 0. So this is -1. And at x square cube, we find that x equals to 0, x plus 3 multiplied with, or that is x, x minus 2 square. You'll find that this is not infinity. That means this is also some, or like, let me write some finite value will get. So that means, so x equals to 0 is a regular type singular point. For now, you check for xp at x equals to 2, the other singular point. Then here you will see that that this will basically give you no, like this is, you have to calculate x minus 2, because that is what you have to check in this condition, x minus a p and x minus a square q. So x minus a, that is a is 2, earlier it was 0, so that's why we were writing xp, but now it is x minus 2 multiplied with p, and you are checking at x equals to 2, so that will give you 2x x minus 2. So you are checking at x equals to 2, you will see that 2 by x. So this is also like, this will also give you 1. So it is not infinity. X minus 2 square q also, you will check same way. You will find that uh, this will be also something 5 by 2. So that's why like here x equals to 2 is also a regular singular point. So you have two regular single points. In any one of the case, like you find like it is giving you infinity, then that would be a irregular single. But here that is not the case. So now, using this series solution method, like how can you solve the differential equations uh, involving around singularity, a regular singularity. So the technique is well known, and that is given by Frobenius, that is Frobenius method. So what you do earlier, the answers that you were taking, there you have to modify a bit, where you have to pick a, uh, a, a factor of x to the power n, and that is multiplied with this whole series, and this is basically the notation in terms of in using this summation. So and then follow the same steps like what we were doing basically before, and this m is basically some uh, value that is determined by substituting your y prime and y double prime in the differential equation. Like after when you substitute, you will get it. You get a basically a quadratic equation of m that is known as individual equation. So this individual equation will give you two values of m, and based on the two values of m, you will write your final solution. Like for example, if your two values of m are something m1 and m2, and they satisfy two conditions, if they satisfy this condition, then you can basically write your final solution to be like this. And if they are m1 and m2 of this form, like for example, m1 is 3 by 2 and m2 is 5 by 2, and your m1 is 2 and m2 is 4. In that case, you can write your final solution like this. So these are some specific conditions where you can how you can write the final form based on m1 and m2. So this again would be are discussed well in your NPTEL lecture. So maybe we can quickly go through a example, like how this all works. Let's say uh, like can solve a question. Solve 3x d square y or dx square plus 2 dy dx plus y equals to 0. So uh, yeah, here you will see that at x equals to 0, you have a regular singular point, singular point. So for about x equals to 0, when you have regular singular point, you can use your Frobenius method to solve this kind of differential equation. So again, you will adopt the same process which we were discussing earlier there before the same thing. So first, you will take your answers, that is k equals to 0 to infinity, k x equals to n plus k. If that is your y, then your y prime, that is dy by dx, will basically will be k 0 to infinity, ak n plus k x to the power n plus k minus 1. And then your double derivative, that is your y double prime, is k equals to 0 to infinity, ak m plus k m plus k minus 1 x to the power m plus k minus 2. So then you substitute this y, all this in the differential equation, y prime and y double prime, and in the differential equation in the, so that will uh, give you a expression in the following way: 3 times of a k m plus k. So I'm just quickly writing this down. You can work out in the same way which we did just previously. The same process you have to use. So ak m plus k x1 m plus k minus 1 plus summation ak x1 m plus k equals to 0. And from here, you will see that like I can further write it as 3 m plus k m plus k minus 1 plus 2 m plus k x to the power m plus k minus 1 plus summation ak m plus k equals to 0. So here the first thing, like the only difference that in this process or in this methodology, like that you would have compared to the last one, is the one where you will determine what is m. So that is obtained from an integral equation, which I was telling you there. This is the integral equation which you have to calculate. So that integral equation, basically you will see that like if you for k equals to 0, for k equals to 0 in this equation, like you have x to the power m minus 1 and x to the power m. So the you have to pick a lowest degree term, that is this the lowest degree term, and its coefficient you have to basically you have to equate it with 0, because in RHS you don't have that coefficient. So RHS is basically 0. So you take the coefficient of x to the power minus m, its coefficient is basically a0 3m m minus 1 plus 2m at k equals to 0. This you should remember. And then basically this is, you can see this is your quadratic type equation. So a0 3m squared minus m is equals to 0. So that means a0 m 3m minus 1 is 0. So your a0 cannot be equals to 0. This means m equals to 0 or 1 by 3. So you got two different values of m, and based on two different values of m, you will determine like two solution, and that will be your final you see right here. So this is the case. So you get two different values of m1 and m2, two different values of m, and your final value would be something of this form, a final solution of a differential equation. So so I can just quickly tell you like what this will be after all. um, uh, yeah, once you get two values of m, then basically you uh, mm, you get values of m here, and then there is one more coefficient where you can also set it equal to 0, that is the coefficient of x to the power m. So so if that, when you will do the coefficient of x to the power m, you will see that there you will get a1 3m plus 1 m plus 2 m plus 1 plus a0 equals to 0. So from here, you basically will get a1 equals to minus 1 em plus 2 m plus 1 a0. So so now you can basically use your values of different values of m. So before that, the last thing is like the recurrence relation. So that recurrence relation you can get recurrence relation that you will get by setting coefficient of x. So you set coefficient of x to the power m plus k to 0. That will give you the recurrence relation. So I'm writing that recurrence relation, that is minus 1 over m plus k plus 1 3m plus 3k plus 2 ak. So yeah, so from this recurrence relation, again you will get different. For k equals to 0, you will get a1 to be something minus 1, m plus 1, 3m plus 2, and a0, and so on. You can write other, I mean, you can write a2 and a3. So that is for k equals to 1 and k equals to 2. So yeah, the same you will do like before what we did. And then for you will get two separate a1, a2, a3 sets. That is like for one corresponding to m equals to 0, because we had two different values, two allowed values of m, that is m equals to 0 and m equals to 1 by 3. So for m equals to 0, you will get something a1 to be plus 1 a0, then a2 1 by 20 a0, and a3 to be minus 140 a0. So that will give you y1. So a0 1 minus x plus 20x square and so on. Similarly for m equals to uh, 1/3, you will also get different values of a1 and a2 and so on. So again here also you will get a uh, another solution. A0 a2 equals to 1 by 56 a0, and a3 equals to, you'll get something. So your final solution will be the superposition of two, since we are all dealing with uh, linear ODs. So your final solution would be something of this form. You will find it minus x by 480 plus 12 plus b naught x cube 1 minus x by 4 plus x squared by 56 plus x cubed by 1680 plus so on. Yeah, that is your final solution. That is how you solve a differential equation about singular points. Coefficients are not constant. Instead, they are some polynomials. So these are how series solution techniques or this methodology is really helpful to us in various ways. So that is what it is all about. So the last part, I know like I went a little too fast. So if there is some problem, like I can try to clarify. Like so, Nachiketa, like was that fine for you, or so? So hello, Nachiketa. Okay, so it was fine for you. Uh, so okay, if you got everything fine, then well, this was our last session for problem solving discussions, and so so you, I think you are about to also appear for an exam in in a few weeks from now. I so I hope you do there well. Like all the best for that test, and then before that test, there will be also one more additional session where we'll try to summarize all the things, or we'll particularly we see if there is any problem or any doubt or any question from your side, and then like we will conclude what basically the story of uh, uh, this course that you have been enrolled for 8 weeks long, or more so. So so that was the last session, and so yeah, if there is any more problem or any other issues, that then you can always reach out to your NPTEL portal where there is a discussion forum. We can try to solve what is there, and also maybe there is one more last meeting among us. We can also meet and discuss any prevailing issues out there. So so that is what for today, and we can see again next time. So okay, maybe we'll see. I think the and then you will have to appear for your test. So all the best for that test, and yeah. So if there is anything to say, like from your side, if not, then you can uh, leave here. Oh, so what will the exam format like? So that exam format, I think, if you would log into your NPTEL page, like there will be the format is already set to. So if you are not able to find it, like maybe I can tell you. So I'm logging to your portal. So so I think like there was a pattern like set by NPTEL, so where you get the format exactly how it will appear in your exam. So I'm just checking it once more, like whether that is still available. Yeah, you will see that once you like log into your NPTEL portal, you will find that there is a exam format March 2024, uh, where you can like here it is written, mm, type of exam will be available in the list. So maybe I can um, copy that link to you where you can find it. So this one online computer test. So so you can get the details there. Basically, like I'm pasting that link. Actually, this link doesn't have much information. I think. Oh, like the portal had information about testing. Okay, so there is no information about exam format and your number of questions. Okay, yeah, that I also am not really aware of it, like because nothing has been said by them about those pattern. If there is so any update, like we'll let you know, or like in meanwhile you can also ask, or you can mail it to NPTEL, like where basically you get all your emails. Then there also you can ask them, and they will let you know what would be the exact format. So as of now, they haven't said any particular format to any of us. So like yeah, that one thing which was you were also telling, like they have said the type of exam would be computer based or the other way, but nothing has been spoken about that yet. Yeah, but if there is any update, like I will try to let you know. So, so anything more, or how was this course for you? Like, was it fine? Like, did you really enjoyed it, or did you gain any fair amount of skills that you were looking? So, like, then it's fine.
The course was actually pretty helpful.
Helpful. Okay. Okay.
But
So,
I think I felt that it was like kind of rigorous. Uh,
uh, y- I see. I see. It is bit rigorous because like this is a very short time. Like in a 8 week, you are learning a lot of things, and you're learning a lot of topics. So that is understandable. But you will see that all these topics are really important. You will find it like if you would go on your future studies, like in particular if you are looking in physics and mathematics, then this is going to be a really a plus point for you, because you have all this information already in some way, at least in some form. And yeah, yeah, I can understand it was bit rigorous, but otherwise, like you find it well, or there were or it was overall something problematic for you.
no, it wasn't problematic. It was really helpful.
Okay, okay. So then that's good. That's good. So like, could I know like what you basically do? Like, what you study?
I'm first year BSc physics student.
Oh, okay. BSFX first. Okay.
Yeah,
Yeah. So like
I study
from
in
hmm,
Azim Premji University.
which university?
Azim Premji University.
NG University. Acha. Okay, okay. All right. So good. So then, yeah. If you find this course well for you, like because if you continue doing physics, then this is going to be really really helpful for you. That is this the course structure that has been designed is absolutely a vital one in future. But yeah, something could have been better, like this. Like as you were telling, like this was a bit too rigorous. Like we could have like gone into more detail and a more slow pace, but otherwise that is fine. That is mm, a small term based course, that is a week 8, a total of week 8 uh, were there. So I mean 8 weeks course, and the topics which were there, like quite something uh, more than substantial, or like I can understand your problem. So yeah, but uh, that was the last session for us. And so anything more to say, like, or
No, I don't have anything.
okay, so then that's fine. So thanks for your presence. So then again, we can see for one more time. That is the next time where we'll conclude various things, and that will be the end of your course, and also for problem solving session. So we had a pretty good time. So that's it. Then we can wait next time. So we can end our session right here. So for today's for this evening, it is all right. So we can end it if you have no further things to add.
I had one more question. Like
Ah,
this is
sure, sure.
this is part one of the course, right? Like there will be one more course, like
Yeah,
mathematical
yeah,
methods in two.
yeah. Oh, mathematical methods too. Are you speaking about mathematical methods too?
Yeah, yeah.
Mathematical methods too. Yeah, there will be like maybe a new course that will I think that will float in future. I'm not sure at what time, but surely NPTEL will do that mathematical methods too. So where you will see that some of the topics will be extension of the topics that we have been discussing right here, and some more new topics, some advanced topics will also appear there. So that will be your mathematical methods too.
So it will be uh, will it start from August?
August, you have to check the schedule. I am not sure about that schedule, like when that will be coming. Uh, like again, like if you really want to know, like you can check the schedule on their website. Somewhere they would have mentioned it, or if not, then again you can mail them. You can ask them. Like so, or it's like if I can also find it, like I will try to remember this, and if I would, able to find this, then I will let you know. Like when the mathematical methods too will also come. I mean, when that registration will begin.
Yeah, thank you.
Okay, so then we can stop here. So it's also already over the time. So we can meet next week, and that's it. So that's it for now. Like so, thanks.